So in this video we're looking at multimedia and how we store graphics and sound on computers. It's part of data representation for A-level computer science, and this is 1.2 in the CIE spec. First of all, we look at how we store graphics, and one way of storing graphics is as a bitmap. So bitmap graphics are images that are made up of pixels. The word pixel itself comes from two words, picture and element, and they were joined together to make pixel. So for each pixel, we need to know what color it should be and where it is. The color is the thing that we need to store. The position is just given by the fact that we store the data in order from top left, pixel by pixel by pixel, all the way down through to the bottom right-hand corner. So the color value is stored as a binary number, and we can assign different number of bits to store that, which means that we can have different numbers of colors. In a bitmap, you'll find a file header which contains metadata. Now remember, metadata is just data about data. So in this case, it's data about the image itself. That could contain things like the width, the height, color depth. That's how many bits we use for every pixel. What compression was used, how big the file is, and so on. And you see on the right-hand side there's an example of an image, and it's showing the metadata about the image. So as well as the file header, you actually have the image pixel data, and that's the binary numbers for every single pixel in the image. Image resolution can mean a couple of different things. In our context, we normally mean the number of pixels in the width and the height multiplied by together. Multiply those two together and you get the image resolution. That's the total number of pixels in the image. So a high resolution image has a large number of pixels compared to a low resolution. However, some people do refer to resolution meaning screen resolution, and that's how many pixels you can actually fit in a certain area, normally measured in pixels per inch. So it's how many pixels you actually physically squeeze into an area of a screen. Those two things are very different concepts, and like I say, the one that we need to really know about and use mostly is the first one. If you have a high resolution, i.e. more pixels in the image, then you can have more detail, but it also means that the file gets larger because we have to store data for more pixels. The color depth is how many bits we assign to every pixel to store its color. It's either called color depth or bit depth. They do mean the same thing. In a 1-bit color depth image, we can only have two colors effectively, black and white, or a pair. But one of those has to be black because the screens are black, and off and no color has to be black. And that gives you one color like white or green that you can actually use to see things with. In an 8-bit color depth image, we can have 256 colors because we can have a color represented by 0 all the way up to 8 ones, binary for 256. Sorry, binary for 255, and including 0 makes 256 different colors. If we store a 24-bit image, which is very common in computing, we use 8 bits per color with red, green, and blue. And if we use 8 bits for each one, and if we multiply that out for 256 times 256 times 256, we get about 16.7 million different possible colors. Sometimes this is referred to as true color. Having that sort of bit depth allows you to have very realistic images with very many colors to cope with an image. So if you increase the color depth, you have better quality, you can have a more realistic image, but again, you end up with a larger file size because you have to store more bits for every single pixel. One of the things you need to be able to do is calculate the size of a bitmap image. And the first thing we need to find out is the resolution. So it's the width times the height. so we know how many pixels there are, but we also need to know the color depth because we have to store a certain size number for every single one of those pixels. So we multiply the width, the height, and the color depth, and we get the size in bits if your color depth is measured in bits, which it normally is. Then you might have to convert it into bytes, so divided by 8, so dividing the number of bits by 8 to get bytes. And then they may ask you to put it in certain units, like a megabyte or megabyte, so you have to do the conversion as well. So for example, if you had a picture that was 800 by 600 pixels with a 24-bit color depth, we would do 800 times 600 times 24, and then we can convert that. Okay, you may get asked what happens when you change image elements like resolution and color depth. So if you increase the resolution, you have a more detailed, sharper image, i.e. less blurry, less pixelation, but you end up with a larger file size. If you increase color depth, you can have smoother graduation of colors, you can have more realistic images, but again, you end up with a larger file. And if you decrease either of those, then you could have loss of detail, but you end up with smaller files. The other way that's typically used to store graphics is a vector graphic. So instead of bitmaps, we're using vector graphics. A vector graphic image is one that's created from a list of drawing objects. So we have a drawing list, and in that list there's every single object called a drawing object that we need to have. Those objects are things like lines and shapes and text, and these are all defined mathematically. For every single object, we need to know the position, the color of lines, things like the fill color, thickness, and so on. So everything we need to know about a shape needs to be defined within the drawing list. There are advantages of vector graphics over bitmaps. One of the major advantages is that they're scalable. So you can make them bigger and bigger and bigger, and you don't lose quality. With bitmaps, there's a fixed number of pixels in the image, and when you make the image bigger, you effectively just make the size of pixel bigger, so eventually you start seeing the square edges of pixels, and that's called pixelation. It also gives you small image sizes. The file sizes are small for things like logos and diagrams. Because there isn't a lot of detail, we don't need to store pixel information for every single pixel where the color would be the same. So a simple logo shape, a diagram, can be a much smaller file size compared to a bitmap of the same thing. And it is easier to edit individual elements. All the objects are preserved, whether they're in the foreground, background, overlapping something else, then they're still all there and they're still complete. It's just you may not see them all. Bitmaps, by comparison, are kind of destructive. So when you put a circle on top of the square, some of that square is destroyed. The pixels no longer exist for that square. You can't undo it once you've flattened that kind of image. Obviously, if you're using layers in something like Photoshop, you can still maintain layers. But in vector graphics, every single individual object is preserved. Obviously, it's not suitable for detailed photorealistic images. You just can't have every single pixel or many pixels being completely different and unrelated to others with this kind of mathematical way of defining objects. It would make much more sense to store that as a bitmap. So bitmap, which is sometimes called raster graphics, we use those for photographs, for complex color gradients. You use pixel-based editing tools like Photoshop. Obviously, Photoshop can do both vector and raster graphics or bitmap graphics. In some cases, for example, with text, it's done as vector in Photoshop initially. Vector, we use it for logos, simple diagrams, technical drawings, and it may be edited in separate software like Illustrator. So now we look at sound and how we store sound on a computer. One of the issues we have with sound, first of all, is it's an analog signal. So it's continuously changing. Um, there's no gaps as such. So we can't really store sound as it's really exists, because that would be an almost infinite amount of information to store. And we have a very finite amount of storage on a computer. So we need some way of converting this analog signal into a digital signal. And the way we do that is by sampling. So sampling just means take a measurement of something at a regular interval. And in this case, we're going to be measuring the amplitude of the sound. We don't measure frequency directly or anything like that. We just measure how loud the amplitude is at our intervals. So once we've measured the sound amplitude, we need to store that as a binary number. So that's called the encoding part. We sample and then we encode. And the bit depth for sound is how many bits we allocate to each measurement of amplitude. Obviously, we have to pick how many bits we're going to use for all of the samples and have it consistent. But once we've set that, then every single time we do a sample, we record a number with that many bits. So some terms that we use for this: the sampling rate is how many samples we take in a second. And like a lot of things that you measure in terms of how many times you've done it per second, we measure that in hertz. That's the frequency. How often do we measure in hertz? We also need to know what's called the sampling resolution, or bit depth, and that's the number of bits for every single sample. This process of going from analog to digital is called an analog to digital conversion, or ADC. That converts analog into digital, and then the reverse, DAC, converts digital back to analog. For example, when you're doing audio back into sound, when you are playing it through a speaker, we're creating analog sound waves again. So if we increase sample rate, make a higher sampling rate, then we get more detail, we got less gaps, so we have better quality. Imagine you had a very slow sampling rate, then the gaps in the sound would become unnoticeable and the quality would be bad. If we increase the sampling rate, we get rid of gaps and we make it more accurate, but we end up having a larger file size because we're storing so many more numbers. CDs, for example, sample at a frequency of 44,100 times every second. So you can see it's very often, there's very little gap in sound, and that's enough for human hearing not to realize that there's any gaps, and we've lost lots of information. The sample resolution has an impact as well. If we increase the resolution, then we get more accurate measurement of amplitude and therefore a more faithful reproduction of the sound. Each additional bit that we have doubles the number of possible values we can store. In an 8-bit resolution, we can have 256 possible amplitude values. In 16-bit resolution, we can have 65,500 possible different amplitude values. But again, increasing the sampling rate increases the file size. So again, you need to be able to calculate the size of sound files, just like we need to be able to calculate the size of image files, at least for bitmap. So what do we need? We need the sampling rate, how often we sample, the sample resolution, and how long the sound is in seconds. Now you may need to know the number of channels as well, so if there could be more than one channel, for example for stereo sound, we would multiply it by the number of channels. In that case, it would be multiplied by 2. So if you're told, for example, you have a stereo recording recorded with a sample rate of 44.1 kilohertz, it's got 16-bit sample resolution, and it lasts for 60 seconds. So we take the sample rate, 44,100 in this case. We need it per second. So we don't take the 44.1, we need to make it 44,100 first, because that's how many in a second. We multiply that by the 16-bit sample resolution. We multiply that by the length, the duration of the music, which is 60 seconds. Again, keeping it in the right units, seconds and seconds. And then we multiply it by the number of channels, which in this case is 2. And multiply them all together, and you'll get the size of the file in bits, remember. So then you need to divide that by 8 to get it into bytes, and then you need to put it in whatever units you're asked to, for example, megabytes. So, recapping, the higher resolution, higher sample rate will give you better quality but larger files. A lower rate or lower resolution will give you smaller files but lower quality. Here are some key points to remember. Bitmaps, remember we store those with pixels and color data. Vectors, we store drawing objects, the shapes and the properties of them. Resolution and color depth affect the quality and file size for images. Sound quality depends on both the sampling rate and the sample resolution. The file size for images and audio can be calculated just with a few parameters. And in the next section, 1.3, we look at compression methods, which can be used to compress some of these files because they do end up being rather large. Thank you very much.